Start. So welcome
Okay.
everybody to Noyo's Science Series. We're excited about having you all here with us tonight, and particularly excited about this talk. I was very pleased to see Gary on our lineup. But before I introduce Gary, I wanted to just welcome you to the Noyo Center and let you know that we're a 501c3 here on the North Coast. If you don't know us very well, we have a couple of facilities now. We have a field station in Noyo Harbor that, Gary, I hope you come up and see sometime and visit us. And the Discovery Center and the Crow's Nest are our exhibit spaces and visitor centers. So make sure when you're in town, you come visit us at one of our locations. We're working all the time to address, we've been focused so heavily on the kelp forest issues that I almost feel like we've shortchanged sea level rise and coastal inundation issues, which is a really big part of our story as well. So it's good that we're getting Gary here and we start to elevate this conversation locally. So with that, I'm going to introduce Gary Griggs. I'm very excited to introduce Gary. He is the go-to guy for coastal process issues on the coast. When I was working for the state of California, we had some very robust and surprisingly complex conversations on what is California shoreline, or really what should be California shoreline. And he spent most of his career kind of working on those issues alone. He's a distinguished professor of Earth and Planetary Sciences at the University of Santa Cruz, and the many accolades can go on. I hope you take a look at the full bio on our website because it is certainly impressive. He has been called a coastal hero by our Coastal Commission as well as Sunset Magazine, and I would certainly agree with that. Gary is the guy when you need to talk about erosion, coastal inundation, or sediment processes. He's the guy. He's the first guy you call. So I'm super excited and really interested to see in the years since we've talked where the science is going. So with that, I will introduce Gary Griggs, our speaker of the evening.
Thanks very much for all of you who are joining. And title is pretty self-explanatory. We have a big challenge, and it's the interrelated issues of climate change, which is raising sea level and what that's doing to the coastline. So this photo is of Pacifica, and the 3 apartment buildings on the left have now been demolished. And this is one of California's environments at threat, not unlike Mendocino and Fort Bragg, which are these uplifted marine terraces anywhere from 10 to 20, 30 to 100 feet in height that are retreating as sea level rises and get hit by storm waves. And this is the other one, low-lying areas, which are being more frequently flooded with high tides and large waves. This is the Embarcadero in San Francisco, and there's a lot of buildings not too far inland from here. You can see the ferry building in the background, and this is without any sea level rise, which is coming. We're not alone. This is Miami, and I don't know. I just like this picture because I'm trying to figure out what he's doing, and I think he wants to park his boat here, but he's got to get a parking sticker for it. So Miami is in even more trouble than we are because it's very low lying, and they also have hurricanes. So 1965, wow, a long time ago, I was starting graduate school at Oregon State University, and we were up in the North Pacific. This was my sort of first beginning of climate change. And we were on a ship going offshore, collecting sediment cores from the deep ocean floor there, maybe 10 to 12,000 feet deep. And essentially you're dropping a long steel pipe with a plastic liner in it and a heavy weight. And as that goes into the seafloor, if everything works, you extract a core of sediment. And we've done that all over the world now. This isn't drilling, it's just using gravity to drive this into the seafloor. And we might get 10, 15, 20, maybe up to 30 feet of sediment. And what I was working on was trying to figure out what the story was being told. And so we get a lot of different kinds of sediment. And as we sort of wash out the clay, what we were finding off the coast of Oregon, about 200 miles offshore, was in the surface sediments, and we could date these with carbon-14 and a few other methods. We found the surface sediments were characterized by a kind of silicious animal that leaves a shell that's very delicate. These are microscopic. And as we got down into the end of the last ice age, the type of fauna changed to a more cold water organism called a planktonic foraminifera. It looks sort of like a bunch of golf balls stuck together. So we could actually go down, and by just counting the number of each of these, we could see if we were in cold water or warm water or what kind of climate we were in. And now we've done climate change studies all over the place. We've looked now by drilling into the ocean floor that we've been doing for 60 or so years. We've gone back 65 million years into the seafloor all over the planet, and we can see the fossil record. We can use the isotopic signatures of oxygen, long history. We've now been drilling into the ice in Antarctica and Greenland, and we've gone back about 850,000 years. And it turns out as snow falls, it's sort of fluffy to begin with, and it actually incorporates molecules of air, the atmosphere at the time. And as the ice freezes, it preserves those little air bubbles. And we can now go into those cores that we've extracted and look at the chemistry of those air bubbles from 100,000, 200,000 years ago. Down in southeastern California in the White Mountains, we have bristlecone pine that can live as long as 5,000 years. And their tree rings, their growth patterns, we can actually look at moisture, temperature changes. And then off the coast here, we actually have deep water solitary coral. These aren't reef building, but solitary coral. And they have a stem, something like a tree, and they'll put on annual rings, and those record the chemistry of the overlying ocean water. So another of several methods that we can tell climate change. And we know the climate of the Earth has been changing ever since we've had an Earth, not just since humans have been around. And what has driven a lot of the older climate change is a pattern we still are witnessing today. So it turns out the Earth's orbit around the sun plays a major role in causing climate change because that changes over time. And when we get a little closer, the climate on the Earth gets a little warmer. We get a little further away, it's a little cooler. And there are 3 cycles that we've recognized, and we've known about this for a couple hundred years. Turns out our orbit around the sun is an ellipse, not a circle. So we get further away and closer, and there's a cycle of about 100,000 years. The Earth also has a tilt, and that's what gives us the seasons. So when we're in the northern hemisphere, our winter is when we're tilted away from the sun. And when we're over on the opposite side, we're tilted towards the sun, and we have summer. And that tilt changes over about 2.5 degrees. So that changes a little bit the amount of heat we get. The Earth also has a wobble, like a top, and that has a cycle of somewhere around 26,000 years. So those 3 are all affecting how much heat we get, what our climate's going to be like. And it turns out we now believe, took us a while to figure this out, that the Earth's about 4.5 billion years old. And about maybe 100 million years after it formed, still pretty much hot and molten. We believe now that it was hit by a smaller planet about the size of Mars. And when that happened, several things happened, and we've even given it a name, Theia. The collision put a lot of the heavier nickel and iron elements into the core of the Earth. The lighter elements, in part, were sort of blown off, and those particles under gravitational attraction came together to form the moon. Some of the surface material, the lighter material, went with it, so our continents don't quite cover the Earth, but it also threw the Earth off of its perfect vertical axis. So that gave us the wobble and the tilt and this eccentric orbit. So there's a natural history behind climate change. In our drilling into the ice, again, we've gone back about 800,000 years, gone back about 2 miles, and that is not a simple thing to do. As Antarctica is one of the only continent I have not been to, but one of my colleagues works there, and it's really cold. The conditions are really rough. You got to drill in these freezing conditions, bring back these cores of ice, and then extract these bubbles. And we can then probe those bubbles, and we can measure the amount of carbon dioxide in those ancient air bubbles. So we know about 80% of the atmosphere is nitrogen, almost 20% is oxygen, and then there's small amounts of other things. Carbon dioxide, it's in parts per million. And if we go back and look at the last 800 or so thousand years, we can see the amount of carbon dioxide, which is a greenhouse gas. We can think of that as a pollutant. It's gone from about 175 parts per thousand to about 275 parts per thousand over that 850,000 years. Today it's up to about 420. So it's gone up about 50%. And if you look at this record, you can see there's these pretty regular peaks. Those are about 100,000 years spacings. And those are from that eccentric orbit of the Earth around the sun, as well as those other variations. And it turns out there's some natural cycles. When those natural cycles heat and cool the Earth, there's some feedback mechanisms. So when it starts to get warmer, the ocean will give off carbon dioxide. The floating sea ice in the Arctic and the Antarctic will melt back, and so the ocean absorbs more heat rather than the ice reflecting it, tends to make the planet a little warmer. And also, as the permafrost thaws, it gives off methane, which is a greenhouse gas. So when we hit a warm period, there's sort of these feedback mechanisms, and then when things starts to get cold, those processes reverse. So these are carbon dioxide being given off during those warm periods. So back in the mid-50s, a bright guy, Roger Revelle, who was the director of Scripps Institution of Oceanography at the time, was sort of a paleoclimate guy, oceanographer. He realized that carbon dioxide was probably increasing in the atmosphere. We knew it was a greenhouse gas, but we hadn't been tracking it. So he sent a young guy to Mauna Loa in Hawaii to set up an observatory and measure carbon dioxide constantly. Why Mauna Loa? Well, it was a nice place to work. Scripps was a nice place also in La Jolla, but there isn't a lot of industry, so we're getting a pretty good atmospheric signature. And what you can see is in that, almost 75-year record, first we could see these are seasonal changes. So during the spring and summer, when plants are growing, they take some CO2 out of the atmosphere. During the other time of the year, we're using up or giving off carbon dioxide as the plants photosynthesize. So not only is it very seasonally, but you can see the increase in the slope of that curve. We can also now see what carbon dioxide emissions have done over time. So what's in the atmosphere is due to not only the natural amount, which we could find in the ice, but also what we've added to it. So this was in millions of metric tons. That measurement doesn't matter, but what we can see is since 1940, when we began measuring it, the amount of the atmosphere that we're putting, or the amount we're putting in every year, is increasing. Interesting little dip here, and that was COVID. People quit flying and traveling and things shut down, so the amount being emitted went down. This is another way to look at it, going back further in time to 1750, and you can see under natural conditions, early civilization, there wasn't a lot of industry. We weren't emitting much carbon dioxide, but beginning with the Industrial Revolution, first burning coal, and then oil, and then natural gas, that amount we emit now, about 35 billion tons a year, is continued to rise. And again, this is only to 2021. You can see that's COVID, and now it's going back up again. So this is what's driving this. And this is just looking at who's producing it. And it turns out the US, not surprisingly, with our industry, was the biggest emitter. And then beginning in the 50s, we began to be drop off. So we're now emitting much less. China has now overtaken us. So right now, if we look at the total amount, China produces about a third. We produce about half of that. And between India, Russia, China, we produce probably, well over half of all the carbon dioxide, probably 2/3. So the concept of greenhouse gas is not new. And actually, this Swedish chemist who won a Nobel Prize for something else, but in 1896, he sort of publicized the fact that carbon dioxide, actually like putting a blanket on your bed, it traps the heat coming from the earth. We actually have a natural greenhouse effect independent of human activity. There's carbon dioxide in the atmosphere, which we said pre-human and industrial revolution was about 175, 275 parts per million. We have methane, we have nitrous oxide. Those produce an average carbon dioxide, or an average global temperature about 60 degrees Fahrenheit if we averaged everything on the planet. Without those natural greenhouse gases, temperature would be about 0. So those gases are a benefit to us, but that's a physical science. It's not political science. And if we go back, for some reason, at about 1880 is when we started measuring global temperatures, measuring atmospheric composition. And we can see this red-orange line is the temperature of the Earth. We can see it going up here in tenths of a degree, averaging global temperatures. And we can see CO2 content increasing. In fact, those are both continuing to increase. This only goes up to 2013. And if we look at sea level rise, this is also going from 1880 up to about the present. It's tracking that same curve. So more CO2 heats the ocean. Ocean heating up expands, and it also melts land ice. And all land ice melts at about 32 degrees Fahrenheit. It doesn't matter if you're a Democrat or Republican. So early on in the last century, in the actually from the 1880s to about 1993, we were measuring sea level rise from tide gauges. These are water level recorders set on a breakwater, a pier, rock, but those are giving us relative sea level. In other words, how high sea level is rising relative to land. So if the land is rising, sea level is rising not as fast, sea level is actually dropping relative to the land. And that's what's happening in places like Alaska that was submerged under thousands of feet of ice. It depressed the land. The ice is now melted since the ice age ended. The land is rebounding, sort of like sitting on your mattress. You get up, the mattress rebounds, only the earth takes a lot longer. So other places like New Orleans are sinking, so that relative rate is much higher. In 1993, we actually figured out how to measure sea level rise from space, and we could get an absolute number. I'll mention here in a second. So while we give Arrhenius the credit for greenhouse gas, it turns out there was a Scotch guy, John Tyndall, who actually discovered this earlier in 1859. And this woman, chemist Eunice Foote, actually discovered this 3 years earlier. At that time, it was very difficult for women to be involved in science and publish anything, but she did this, and she did some laboratory experiments, and she basically laid out the fact that greenhouse gases are occurring, and they're going to, warm the atmosphere. So we need to give her credit. So where is all that carbon dioxide coming from? Fossil fuels and cement, over 90%. And most people don't realize that as we make cement and then put that into concrete, that takes up about 6 or 8% of all the carbon dioxide is produced by making cement. So we take limestone and we heat it in kilns, and limestone is calcium carbonate. And when we heat it, we drive off carbon dioxide and are ended up with lime, which is calcium oxide, the building block of cement. So around the world today, particularly in China and India, this is a huge source of carbon dioxide. Most of the rest is from land use, burning the rainforest, cutting down trees, forest fires. Where does it go? Roughly half goes into the atmosphere. About a quarter of it is taken up by plants on land, and about a quarter of it goes into the ocean. About a little over 1 million tons per hour, and that is actually making, because of chemistry, the ocean more acidic, which is a whole different topic in terms of coral reefs and those organisms that make shells being threatened now by a more acidic ocean. So probably you have read or seen such figures, but from our temperature measurements going back to about 1880, we have now seen that, in fact, if we look at the average from 1900 to 2000, that would be this black line. This is global ocean and land temperature. And all these other blue or red are anomalies. In other words, they're either colder than that or warmer than that based on that 100-year average. So what we can see is the planet's getting warmer every year, and 2023 was the warmest year in at least 140 years, and we think maybe several thousand years at least. And last year was a big bump up. So this is a NOAA, or it might be NASA, I'm not sure. This is sort of a little video of global temperatures over the period from 1880 to the early 1900s. And you can see, again, this is the anomaly or the difference between the long-term average. So any place that's orange or red is a little warmer than average, and the blue is going to be colder than average. So this is going to go, you'll see on the bottom what year we're at, and then how these colors will change as we progress. So we start to get into the later 1900s, more burning of oil and coal and gas, and particularly we see the temperature getting warmer in the high latitudes, the Arctic, say. So this gets us up to 2015. Warming significantly faster than the rest of the planet. And this is where a lot of the ice is in Greenland and Antarctica that's melting. So if we go back, looking at those ice cores, looking at sediment cores, we can get an idea of climate change and also how sea level has fluctuated. So sea level is directly related to Earth temperature because, again, we're expanding the ocean as it warms or contracting as it cools, and we're melting more ice or freezing more ice. So if we go back, this is about 375,000 years ago up to the present. This is where sea level was relative today in meters. So by convention, we call sea level zero today. But if we'd been around any other time in the last 375,000 years, sea level would have been someplace else. It's been as low as about 125 meters or 400 feet lower than today. And it's been higher than today. So these are these ice age cycles. This is also the 100,000-year cycle of the Earth eccentric orbit around the sun. And these are sort of these that 40,000 and those other cycles because they're not all aligned. So what we see is temperature warms up pretty quickly and sea level rises pretty quickly. And then it drops off over about 100,000 years. So that's sort of a typical sort of human alteration cycle. And we can take these back, several million years. These are these ice ages. When we have an ice age, ocean water is transferred to the continents as ice sheets and glaciers. We took about 3% of the ocean out during these ice ages. Maybe 3 million cubic miles of ocean became ice, and sea level dropped each time about 400 feet. So that was the last ice age, ended about 18 to 20,000 years ago, and then it came up to where it is today. So if we were to look at the offshore water depths, here's the Golden Gate. So this would be the edge of the continental shelf. That's how far sea level was offshore. These are the Farallones. We could have, if we walked briskly, we could have, gone out to the Farallones for lunch. That was all dry land 18,000 years ago. And then as sea level rose, the climate warmed, ice melted, we raised sea level 400 feet. So the shoreline retreated at about a little over 7 feet per year here at San Francisco. I just pulled off Google Earth Fort Bragg. The shelf here is quite narrow. I think I thought I put that in. It's about 5 miles offshore. So here, sea level rose same rate, but the shoreline was not so far offshore. So the beach would have been about 5 miles offshore 18,000 years ago. If we just look at the last 20,000 years, so this is where sea level was, 390, 400 feet below the present. This is 20,000 years ago. Here's 0 today, and there's 0 sea level. Sea level rose when the ice age melted, or the ice age ended. Ice melt, seawater expanded fairly rapidly from about 18,000 to maybe 6,000 or 8,000 years ago. About a half an inch a year, or 45 inches per century. Within that, though, there were some steps in here, and we believe now that these are periods of ice sheet collapse in Antarctica, and that's something we're starting to see happening today. So these ice sheets started to break up and surged into the ocean, raising sea level. So during these surges, about an inch a year or 8 feet per 100 years, pretty fast. And then about 6,000 years ago, sea level pretty much ground to a halt. In a normal cycle, that would have been the end of this warm period, and it would have started to drop off and get cold again, and we'd go into another glacial period, maybe less than a millimeter per year. However, that's the rate we're seeing today. About over the last decade, about 5 millimeters per year or 20 inches per century. Not as fast as the past here, but that rate is accelerating, again, with more greenhouse gases in the atmosphere. And the question is, how fast is it going to continue to rise, and what level will we reach at various points in the future? 2030, 2050? And I will say that this may be the biggest challenge human civilization has ever had to face, because this is about the beginning of human civilization, 6,000 to 8,000 years ago. All of civilization developed when sea level was stable. So we started out with coastal settlements, and then villages, and then towns, and then cities, and now megacities when sea level was level. And now it's changing. So this is a short little video of what's happening around San Francisco over the last 18,000 years. That's the shoreline moving landward as the ice melted, goes into the Golden Gate about 7,000 years ago, all the way to Sacramento. In fact, what many people don't realize is Sacramento is actually an ocean port. We have ships that go all the way to Sacramento to pick up rice and other stuff. So sea level is not just an issue here, but 100 miles inland, we're at sea level. So as I said, in 1993, after using tide gauges for many, many years, over a century, that were getting relative numbers, some really smart people figured out we could measure this from space. So they sent up two satellites, Jason and Poseidon, and what they're doing is essentially sending down radar beams from the ocean surface, I should say from the satellites to the ocean surface, bouncing back and measuring that distance. They have to know exactly where those satellites are, down to 100th of a millimeter. So what they're doing is circling the Earth. You'd think, well, the ocean surface is so irregular, but they're taking millions of elevation measurements. So this is when it began in 1993. And what you can see is if we average that whole 30 years, it's about 3.57 millimeters a year or 14 inches per century. But again, that rate is accelerating in part because of what we're putting into the atmosphere. And it's now close to 20 inches per 100 years. But the question is, how much more will that accelerate in the future? So if we look at the ice that can still melt, if we look at the continental glaciers, so this is the Alps, the Andes, the Himalayas, Glacier National Park, which is glaciers are almost gone. We could raise sea level about 2 feet. That's only a problem if you live within 2 feet of sea level, which many people do. If we look at Greenland and we melted all of Greenland and it's melting faster than scientists expect, we could raise sea level another 24 feet. So now we've got 26 feet of sea level rise, and there are lots of places around the planet, many of those in Southeast Asia, India, Bangladesh, China, with people living close to sea level, as well as many communities in San Francisco. Antarctica is the big 800-pound iceberg. We've got 190 feet of potential sea level rise. So if we put those together, we could potentially raise sea level 216 feet. That would probably affect a couple of billion people. We don't need to do that. And nobody thinks it's going to happen this century or next, this year or next. But 5 feet is going to be a problem. So the question is how much more, how soon? And those are things that people are worrying about. As sea level rose, when the last ice age was over, natural coastal environments, coral reefs, mangroves, which live in tropical environments, and eelgrass and so forth, they continued to respond.
Okay, I found this on the web for Hey Sea Level Rose.
Oh, God.
So the natural coast environments quarries mangroves, which live in tropical environments. And
What's that?
I think that's a Google question or something.
Oh my gosh.
That's crazy. Answering my question for me. So while sea level fluctuated hundreds of feet over millions of years, coral reefs continue to be able to grow up, mangroves survive. So natural vegetation, natural environments will do okay. We worry a lot about those today, but they're going to take care of themselves. However, cities, not so much. And I just happened to pick San Francisco and Oakland. Today in the US, there's the US may be 13 million people living within 6 feet of high tide. Globally, about 150 million people living within 3 feet of high tide, because those cities weren't built with sea level rise in mind. So as I started in the beginning thinking about California's coast, there's two types of environments in my first two slides. One are the cliffs and bluffs, and this is a Pacific again. You can see these tiebacks that were meant to hold the cliff together, which didn't. The higher the sea level is, the more energetic the waves, and it looks like waves are getting bigger, the more erosion at the base of the cliffs and the bluffs is going to occur. For low-lying areas like the Embarcadero in San Francisco or Miami, New Orleans, New York, Charleston, Shanghai, Guangzhou, Dhaka, Singapore, they're going to be temporarily flooded more and more often, and at some point permanently inundated. So those are the two big problems. SFO was originally a cow pasture, a low-lying sort of a muddy cow pasture. They brought in fill, raised it to about 2 feet above high tide. They were not concerned back in the 30s and the 40s with sea level rise. So there's a problem there, as there is Oakland. Most of the nation's airports, big airports, were built in coastal cities out over the water because there wasn't any land left over. So if you look at Boston, Logan, LaGuardia, Miami, they're all out over the water. So this was originally what was called Mills Field, which was San Francisco Airport. There's a great website called Surging Seas, and you can go on this and look at any place. And what it shows is, using the most up-to-date topography of the land, you can actually raise sea level. So this is high tide. You can raise sea level 1 foot at a time. So here's SFO. This would be above high tide, or Oakland. The blue means it's flooded. The green means it's below that elevation, but it's protected by a levee or a dike. So at a foot above highest tides today, parts of SFO go underwater. We can go up to 3 feet. That's sort of the mean or average projection now for where sea level might be in 2100. It could be considerably higher. And Oakland Airport's underwater. And we can go to 5 feet, and this just gets progressively worse. We can go to 10 feet. By 2100, 3 feet, 4 feet, 5 feet is possible. 10 feet is one extreme, but this gives you some idea. This is the Alameda Naval Air Station. How much of our Bay Area is below that elevation? You may know SFO is a huge economic engine, and they have, I mean, it's billions of dollars of income in addition to be this transportation hub. They have proposed a 10-mile long, $587 million seawall that they hope will hold the water back till about 2080. So they're maybe buying that many years of protection. Right now, it's in the environmental impact study phase. This is happening at other places also. This is along the San Francisco waterfront. There's the Bay Bridge, an old seawall, and now my favorite public agency, I'm joking, the Corps of Engineers, which likes to build stuff. They have a $13 billion plan to try to elevate the shoreline here. They're talking about elevating the ferry building. That's going to be a challenge. And then San Mateo County is proposing an $11 billion wall and sort of a lagoon here that they can have gates that they can open and close when the tide comes in. Can they afford $11 billion? Venice has done this, and these floodgates are still sort of questionable. So these are some of the challenges and some of the proposals that have been put forward. You know, you can protect one part, but what happens when it goes around the edge? This would go from the edge of the San Francisco airport, and these are other walls they might have to put in. So this is what's happening today at a king tide. And a king tide sounds, you know, astronomical. It's really just a few tenths of feet higher than our normal high tides. And these happen a couple times a year. It's when the moon is closest to the earth and the earth is closest to the sun in our orbits, and that's when the tides are a little bit exaggerated. So if it's normal high tide is 6.5 feet, king tide might be 6.7 or 8. It's not 2 feet higher, but it's enough, say along the Embarcadero in San Francisco, where people are getting wet. That's a parking lot up near Sausalito. And this is right after you go off of the Golden Gate Bridge. This is if you're going out to Mill Valley and Stinson Beach. So this isn't floodwater, it's high tide at sea level, today's sea level. So we're kind of at a king tide. We're surrounded by these issues. Corps of Engineers, which likes to build stuff, and I think they've made a lot of errors over the years. They have recently proposed an 8-mile long wall around Charleston for $2 billion, $4.5 million around Miami, New York, New Jersey, a 6-mile long wall for $119 billion, and one to protect Houston. And I wrote an article published recently about, is that the best solution? And there's a lot of questions about social equity. Who's included in the protection, who isn't? Is it protecting us against high tides or sea level rise? And I think those are questions we need to ask before we start spending billions. And we discovered in Hurricane Katrina in New Orleans a few years ago that the walls collapsed. So how high can you build a wall and be effective? So this was the storm. It was in the background in my slide up here, my camera. This is what happened in January of last year. Really high tides, really big waves battering the coastline. And I did find one at Noyo Harbor. I think you get your share of really large waves also. Makes a lot of things more difficult. So low-lying communities, this is near Santa Cruz, a little town of Capitola. These are the oldest condominiums on the California coast. They were built in the 20s, but they're built basically at beach level with a little wall here. Much of the downtown area is on sort of the floodplain of Aptos Creek, very low. And this is a little wall along the front. There's those brightly colored condominiums called the Venetian Courts. There's these people sitting out there having their lattes, reading the Wall Street Journal on a nice calm day. And then we get a king tide. So this is happening more and more frequently. This is in December when the downtown was flooded. Waves came through the restaurants, and this has happened 15 times in the last 60 years, and they keep building back again. And one of these brightly colored condominiums on the ocean end, it's sort of like the prow of a ship, was put up for sale a couple of years ago at $4.8 million. Nothing in this real estate ad about where it's located, except it's iconic. And this is that same unit this last winter with the waves coming in. They've come over that little wall. He's trying to put plywood up to block the waves. And when it was done, it just blew out the front of one of those that's been there for almost a century. So bad location. So what's next? Where do we go from here? With climate change and sea level rise, we have 3 options: mitigation, adaptation, and suffering. We're already doing some of each, and the only question is the future mix. The more mitigation we do, which is moving away from fossil fuels as rapidly as we can, cutting down greenhouse gas emissions, the more of that we do, which is going to be a challenge, the less adaptation. We can't all live in houseboats, and the less suffering, fires, storms, and so forth. So right now in the US and globally, about 80% of our energy is provided by coal and natural gas and oil. So while we're, particularly in California, moving to renewables, mainly solar and wind, we've got a ways to go, a long way to go. We're not going to do that overnight. It isn't going to be easy, but quite frankly, it's our only realistic option. There's other things that have been thrown out there, putting mirrors up in the sky and so forth, sucking carbon dioxide out of the atmosphere. I will say, I don't think that's ever going to happen. It's just not practical or feasible or affordable. So I think we have one direction to go. The response or adaptation, we have basically 4 options. Denial or do nothing. Doesn't work. We can add more sand to the beach, which can be short-term and very expensive. We can build walls, seawalls, revetments, or the words that nobody wants to hear. We can relocate, we can move back from the shoreline. So California, we don't do much beach nourishment. There was 2 projects in San Diego where they took sand from offshore, put it on the beach, 3.5 million cubic yards. It cost 46 million, and it was gone in 1 to 2 years. The East Coast does much more of this for a bunch of reasons. Corps of Engineers likes to do it. They have some powerful congressional people. So over the last 90 or so years, they've taken 1.57 billion cubic yards of sand from offshore, put it on the beaches of those Atlantic states at a cost of about $15.4 billion. Federal government pays 2/3 through the Corps of Engineers, and local communities pay the rest. So we've been subsidizing that. Florida alone has had 682 individual nourishment projects, 351 million cubic yards of sand. And if you want to get an idea of that, a typical dump truck holds about 10 cubic yards of sand. So that's 35 million dump truck loads of sand. Palm Beach has had sand added 77 different times. A reasonable person would say that's probably not working, or that's not a very good investment. But these are the kinds of things that the government's protecting by putting more sand on the beaches. And even that's not going to help in many places. So armoring is what's been the most common approach in California for a century. This happens to be in the middle of Monterey Bay, Pajaro Dunes. This is out on West Cliff and Santa Cruz. This is Monterey. This is Solana Beach. Different kinds of walls, rocks, so forth. If we look at the entire coast of California, about 14% has been armored. Southern California, over 1/3 has been armored, and those systems have some impacts. They say that's the end of a century because, by and large, the Coastal Commission, going back to their original documents, said we're not going to do that anymore. We're not going to prove it. But then maybe 2 months ago, Half Moon Bay, homeowners went to court against the California Coastal Commission and said, we want a seawall. The Coastal Commission says, no, that those weren't there when the Coastal Act was passed. You can't get protection. And the judge decided against the Coastal Commission. So that's going to be huge depending on what happens next. This has been sitting out there for a long time, and you can see they had a timber wall. It's not a place where I would invest money. What's been labeled, for better for worse, is managed retreat, the idea of moving back from the coastline. And by and large, most coastal homeowners aren't too excited about that. They hate those words. And 2 reasons, I think. One, the idea of retreat, quitting, giving up is not popular, and nobody wants to be managed. So our choice of words in the beginning wasn't very good. Some people have called it managed relocation, realignment. But in fact, we have been doing this. This is way back in time on the Washington coast. They've moved a house. This is on the East Coast, in a place you may know, Gleason Beach on the Sonoma coast. There was an entire row of homes here that are now gone. Their septic tanks are in the sand behind walls. Those have all been destroyed. Highway 1 was right at the edge, so they basically put in a bypass. The Coastal Commission agreed with Caltrans. It took 10 years. This is, I think, $57 million, but we actually have moved back. Santa Cruz Capitola, there was a series of apartment buildings right on the edge. The foundations were compromised during the Loma Prieta earthquake. Those were demolished. They're no longer there. I would call this maybe unplanned retreat. And some of you either may have gone to school at UC Santa Barbara or know or have children. These are student apartments right on the edge. It's retreating. You can see their caissons are being exposed. This was back in the early 2000s. This is more recently. Said these weren't safe. They've taken off parts of these units. Their decks are gone here, and they've moved back. And I just read a week ago that after a big party on one of these decks, it started to collapse. So they then said this is unsafe to occupy. You know how university students get happy on the weekend, I guess. Broad Beach in Malibu is another place that was built on a sandy beach that's now losing their beach. It was called Broad Beach, no longer. Now they put in rocks that the Coastal Commission says those got to come out of there. You need a permanent solution. I've done a couple of consulting projects here. You may have heard about this beach. It's where a lot of movie people live, including James Bond. This is his house. And when I was named a California coastal hero, they actually named James Bond one of the heroes also. So I got a chance to talk to him. So a lot of people here with a lot of money that could afford to do something, but they are stuck right now without a solution. So what do? We've got places like San Francisco. We've got places like Miami Beach. All over the world, we're sort of in this difficult position, a huge challenge to figure out what we're going to do next. Every community is going to have to deal with this. The East Coast is finding economics are beginning to weigh in because property prices in some of these hurricane hit outer islands are beginning to lose value, not in California. We're also finding that the insurance companies are no longer going to insure some of these homes. So if you can't get insurance, you can't get a mortgage. California is experiencing that with the two biggest home insurance companies because of the fire risk. Insurance companies don't want to lose money. So the state is putting out new reports about every 5 years. This was one done in 2017. I happen to chair that committee, giving us projections for the future. This was some guidance to go along with that. And then we just finished the 2023 report that's out for public comment. So one of the ways of looking at it is going off into the future. What's sea level likely to be like by 2040, 2050, 2100? For my thinking, going back past 2100 doesn't really make a lot of sense because none of us are going to be here. We can't even really comprehend what that's going to be. But based on future greenhouse gas emission scenarios, how much more carbon dioxide goes in the atmosphere, how our power production evolves, we can see different amounts of sea level rise depending on really political issues, not science. So 2050, sort of the average could be a foot or so. By 2100, the midpoints may be 3 feet, but it could be 4 feet or 6 feet or 8 feet. So that presents some real challenges. The closest tide gauge to Fort Bragg is in Arena Cove, and it's actually much less than the global average. This is, again, relative. Global sea level is rising at about 5 millimeters a year. And I think what's happening there is probably the land is slowly being uplifted. So not the same situation that some other areas are facing. And what you can also see, this is the 1997-98 El Nino. This is the 1983 El Nino. That raises sea level as much as a foot or more for months at a time. So those short-term events are going to be more problematic, just like these high tides and storm waves versus long-term sea level, probably for at least till mid-century and maybe beyond. So I'm going to leave you with 5 two-word sentences. It's real, it's bad, it's us. Scientists agree there's hope for California. Thanks very much for your attendance and your attention. And I see there haven't been too many questions, but I think now's the time.
Oh my gosh, I have a million questions, so I'm gonna just, I'm not sure. I'm not sure I'm understand where the hope part comes in. But Gary, when we just bought a building in the harbor, which a number of people have said, how done was that? Because what does managed retreat look like for many of our coastal harbors, like that are dependent on, access to the ocean? And when we're about to undertake sort of a process to like determine what we feel like is a reasonable sort of estimate about what retreat or what like the only thing we could I can see right now is that we jack our building up, right? But how much? Like you just showed us a slide that was 1 to 8 feet. I mean, we can't really jack a building up 8 feet in the harbor and make that. But even jacking a building up, you're just the water's just going into the street. So what's your advice for communities like ours that are looking at resiliency in harbors when we're really dependent on coastal resources and what does
Right.
retreat look like?
Yeah, well, what's interesting that harbors have planned for this over the years, and all of our boat slips can rise and fall. So the slips themselves and the boats are fine. It's all the stuff we built around the edge. And so I think I see a 3-step process for any community. Noyo Harbor, Fort Bragg, San Francisco. The first is the realization that sea level rise and climate change are real, and getting some idea of what future elevations we can expect. The second is, what are the most vulnerable areas? What are the things that are going to get hit the first? And that's partly elevation or exposure. And are those public or private? So if it's a public harbor or a freeway or, Highway 1, like down at Gleason Beach, in some ways it's a little easier. It still costs money, but you're not dealing with a homeowner who doesn't want to believe you. So I think that next step is the vulnerability, and you can see now of all the buildings down there, what is their sort of projected lifespan? And there's some facilities like a huge power plant, a highway, an overpass, a railway that maybe they're projected to last 50 years or 75 years or 100 years. So you want to probably be a little more conservative and go with these higher numbers. And the newest sea level rise coming out, the last one in 2018 used probabilities. Well, there's a 20% chance, there's a 50% chance. We've decided in this one to use scenarios: low, intermediate, low, intermediate, high, and high. And then you can decide based on the facility or the structure how much chance you're willing to take. And then the third step is, how do you respond? How do you adapt? We can raise buildings. That's done, pretty frequently. But you certainly don't want to be building more expensive assets that are going to be exposed within the next 2 or 3 years. I think the tide gauge at Point Arena is probably, Arena Cove is a good one. And because in general, the California coast is rising, these uplifted marine terraces, these benches that you're built on, tells us that it's rising. And there's some work that's been done that can give us the rate of rise. So if we go back to that Arena Cove tide gauge, if we know it's rising at, 1 millimeter per year, and globally it's rising at 5, it's saying the land is rising at 4 millimeters a year. So you've got a lot more freeboard and a lot more time than other cities like New Orleans, for example. So, I mean, that would all be factored in. I actually do a fair amount of consulting for mostly individual homeowners who are trying to figure out what to do, and giving them at least the kind of information, and working for communities too now, as well as the state, on, what are the probabilities, or what are the scenarios, and how do we begin to respond to that? But it's certainly not a simple answer for anybody, but I think it's facing the reality of what's happening.
Well, okay, so not surprisingly, we're getting a lot of questions about armoring the coast. And so I was surprised that you didn't come out a little bit more negative about armoring the coast, since we've seen so many negative impacts to seawalls and breakwaters and stuff. So can you tell us, like, in the reality of what's happening, what the latest thinking about is about seawalls and armoring the coast in general? I mean, I know it starves the beaches and kind of exacerbates the problem in some areas. So what's your thinking lately on that?
Yeah, I didn't talk a lot about that because of the kind of coastal commission stance that we're not going to build any more of those. We might repair old ones, because the Coastal Act said, when it went into effect in January 1, 1977, if an existing structure is threatened, you can apply for a coastal protection permit if you deal with all the impacts. What does an existing structure mean in 1977? For years, property owners and their attorneys argued, well, it's existing now. But part of the Coastal Act also said if you're going to build a house, you need to make sure it's got 100 years of stability without a seawall. So the Coastal Commission was kind of soft on that for years. And they decided, no, we're going back to the original language that says if an existing structure is threatened, if it was built before 1977, you could still apply. But we know I've worked with seawalls for 40 years, and there are some pretty clear effects. There's the visual effects, there's the coastal access effect, there's the cutting off of any sand supply that would have come from the eroding bluff. If it's a pile of rocks or revetment, you take up beach space. Probably the most important is what we call passive erosion. So when sea level was 400 feet lower, the coastline at San Francisco was 25 miles offshore. We had a beach there. We can actually go down to the ocean floor and sample beach sand. As sea level rose, the shoreline moved landward to where it is today. If we had nothing in the way, we would still have a beach, we'd have a bluff, and it would just keep moving inland. But once we build a wall, and that's what's behind me, there are these rocks, sea level is coming up against the bluff or the structure, and we're going to drown the beach or flood the beach. So what we call passive erosion, that's happening in Pacific, it's happening all over the place. So we're protecting private property or public facilities at the expense of the public beach. So there's lots of problems with seawalls. We just built an awful lot of them, and now we've got problems of how do we deal with those structures? They can't last forever, but we're losing beaches for the public where we built those structures. That's filling in the gap I didn't talk about.
Yeah, that's great. That's great. We have a couple more questions about that. But before we get to the questions, I have another one. So like if Gary, if you were the king of the world and you're looking at Lahaina, as tragic as it was that that city burned down, when you're looking at redevelopment of a city like Lahaina, what would you advise? Like, how would you redesign what was there to address some of these issues?
So Hawaii, and I haven't looked at the tide gauge recently for Hawaii, but as you may know, I could give you my whole slide on the Hawaiian Islands or my whole talk, but the Hawaiian Islands are
That'll be part 2.
they're over a hot spot in the mantle.
Right.
And coming up under that hot spot is magma.
Right.
And it erupts today under the Big Island, Hawaii, Kilauea. And the fact there's a new volcano formed down at the southeast corner. So as the plate has moved over that hot spot, sort of like a piece of paper over a candle, we've burned through, volcanoes have formed, but now as we go up the Hawaiian chain, we go from Hawaii to Maui. Maui has Haleakala. It's sinking though. That huge mass of lava on the seafloor is causing Maui to sink slowly. Kauai is sinking. Oahu is sinking. You go all the way up that chain to Midway. The old volcanoes are completely below sea level, and we just have a reef or an atoll left at Midway. And it gets more complicated because it turns and goes all the way up the Aleutian Trench. About 70 million years ago, that was over the hotspot. So Maui has the problem of it's also sinking slowly in addition to sea level rise. So I think what they need to do, and I don't know the elevation of Lahaina, not high, that and certainly it's tied into the ocean there, but it seems to me the most important thing is to develop a sea level rise curve like this or potential scenarios and say, okay, we may have to set back 1,000 feet, a quarter of a mile, and make this an oceanfront park. And you may remember 1964, huge Alaskan tsunami that hit Noyo Harbor also destroyed a bunch of Crescent City. Crescent City actually built an oceanfront park in the area that was flooded, said we're not going to use this. And there are a few buildings. So they, hard as it was, because people want to come back and build. So I would say they need to look carefully in Lahaina at their elevation, their potential for sea level rise. Fire is a whole nother issue. I think those buildings are, pretty lightweight tropical construction. And once that wind started going, I think there's also a number of other fires burning at that same time. We don't think about Hawaii burning, but very tragic.
Yeah. Well, you kind of answered one of the first questions, which was, I mean, you're kind of highlighting how sea level rise is really kind of a complex question depending on where you are. And somebody was asking if volcanic landmass was being considered with some of the modeling. And it sounds like, regionally, when you're looking at your own issues, that is definitely the case.
Yeah.
Yeah. Okay, so again, related to seawalls, revetments, we have a question asked to you about what do you believe is the most sustainable solution to mitigate sea level rise on beaches besides, reducing our fossil fuels?
Well,
You're
and
the-
that's mitigation versus adapting to it. I've written 2 papers recently. One's called "Can We Build Resilient Coastal Cities?" And there's a lot of use of that word today and money being put out to build coastal resiliency plans. I have to say, I've never seen a resilient coastal city on the California coast. I think that word's really comforting because, we can make it resilient, we're all okay. But what does that mean? I guess we could say Sausalito and houseboats are resilient because they can rise and fall with the tides, but clearly all those people living on the shoreline are not going to be able to elevate their houses or beaches. The other thing we're talking a lot about today that I'm questioning is living shorelines. Let's not build seawalls. We're going to plant stuff out there. Well, look at your coast there in Fort Bragg and Mendocino and say, what would you plant there? Well, you can plant stuff up on the bluff, but that's not going to stop the waves and the high tides. So I think that came out of places like the tropics where we have coral reefs that are effective, and we have these mangroves, these trees that can live in salt water that trap sediment. But still, we know when sea level rose, all bets are off. It's going to flood right over that. So to me, I think we can plant stuff in the sand dunes, but that doesn't stop sea level from rising. So I think those need to be carefully considered. I think what we would like is everybody to be able to live in those coastal homes as long as they can. And we want to be able to use our public beaches as long as we can. But where a beach is backed by a wall, which is what happens in Santa Cruz with the boardwalk, we're going to flood that beach. And it's only a question of when. So we need to begin to develop, I'm going to say thresholds or trigger points. We can say, okay, when your house is flooded, I don't know, once a week, once a month, it's time to move back. Your insurance policy lapsed, your house is gone. When you get to within 10 feet of a coastal bluff, like happened in Pacifica, city building department comes out and says, this isn't safe. You got to move it or remove it. So I think we're going to have to set up, and that should take public input, public to agree. Yeah, you're right. At some point, maybe not in my lifetime, I hope not. Maybe my kids and my grandkids aren't going to be able to enjoy it, but we cannot stop sea level from rising anytime soon. And something I've said, which sounds a little harsh, but there is absolutely nothing we can do over the intermediate term, over the long term, to stop sea level from rising, to stop the waves from impacting the coast. Maybe we can do it for 10 years or 20 years or 30 years, but a time will come because of all that greenhouse gas that's in the atmosphere that we've baked in. We can try to slow it down, but all the work that's been done suggests that's going to be really hard. And with 80% of our energy still being produced by fossil fuels, and we can start talking about other source of energy. Do we build nuclear plants, whatever? Offshore wind is maybe coming along in California. So short term, I would look at each case individually and say, okay, what's reasonable, what's affordable, what can we do here? But we can't stop the Pacific Ocean. And it may not be tomorrow or next year or the next year, but we know from the pictures in my background here in Santa Cruz, it was last winter. And
Yeah.
it's going to come back because we know sea levels rising. We know waves seem to be getting larger. Whether we have more El Niños than in the past is a good question. We're not really quite sure, but that's also possible. I hate to be the bearer of grim tides, but I think we also need to be realistic about it. What's coming, and the science is good. Scientists are in agreement on these things.
Well, that was actually one of my questions for you is how confident are you in the models these days with, we had so many assumptions 10 years ago working with you. There were so many assumptions. How now that we've gotten so much, our models have matured so much, how confident are you in
Yeah.
projections these
So I'm
days?
going to come back to this slide. There's this interesting green line here, and I don't know what it is, but it's been
I
on
don't
all
either.
place. So I am not a modeler. I look at data, I look at historic photographs and information. And the people that were on this most recent sea level rise task force that projected these models, they are getting more sophisticated. When I questioned one of my friends about models, he said, Gary, models are all wrong, but maybe some of them are useful. And that could tell us, okay, to get sea level rise and climate, carbon dioxide is important. The cloud cover is important. What's happening in Antarctica is important. How do you put those into mathematical terms? But forgetting the models, this is now 30 years of sea level rise data. So if it just continued at the same rate, it would be 20 inches higher in 100 years.
Yeah.
But this is getting steeper, and actually people have calculated the rate of acceleration, and we can see that again with the rate of carbon dioxide in the atmosphere going up. So without a model, we still know it's going to get worse. And the question is, how much worse, how soon? So I don't understand the models. I'll be perfectly honest about that. But I mean, we model everything today. We model the, economy, the budget, college tuition, cost to retire, property values. So I mean, to me, this is the science. This is factual. This is what we know is happening, and it's increasing.
Definitely. Okay, so Bob is asking a question that I'm not sure I understand, but he says something C14 depletion in CO2 has been used to indicate our contributions to CO2 rise. Is that still a valid indicator?
I'm not sorry. Say that again.
C14 depletion in CO2 has been used to indicate our contributions to CO2 rise. So is that still a valid indicator? Bob, you might want to unmute yourself and ask that if it's been typed in wrong.
Let's see. Maybe I can find the question here.
We lost Bob. Bob, are you around still?
Oh, here. Is carbon-14 depletion in CO2 used to be used to indicate our contribution to CO2 rise? I mean, carbon-14 is a very small amount of total carbon that we use for dating things. It's radioactive, blah, blah, blah. I don't know whether I can answer that. I would think the information we have on carbon dioxide from Mauna Loa is, the best indicator of human contribution.
Yeah.
I think, sorry. I think this is about like C14, right? It only is generated in the atmosphere. So the old carbon that we're burning has depleted. So if the ratio in the sky is getting less, it means a certain percentage is from old carbon we're burning.
I see. And I can't answer that. That's still I'm sure people are working on it, but I don't know the answer to that. Got it. Good point.
Okay, so Amy's asking, she's making the point that we need to have a tide gauge in Noyo, which I would love. But she says maybe a naive question is, for a place like Noyo Harbor, are there good durable examples of floating roadways? Say we raise our buildings, the roadway is still underwater as an alternative to bridges. Is anyone looking at floating roadways? What are some of the I guess the next part of that is, what are some of the more creative things people are looking at?
Well, there's a lot of architects, planners looking at floating cities, but that's really expensive. And I would say floating roadways would come into the same category. what they have done, well, there's the freeway in the North Bay that goes across towards Vallejo, and that floods at every high tide. And there they're going to basically elevate the roadway, put on like the overpass there at I think it's called Scotty's Creek at Gleason Beach. I mean, we do that all over the place. We make bridges over, lakes and rivers and so forth. I think that makes more sense than trying to float the roadway.
Yeah.
Not plain dumb. I always say there's no dumb questions, they're just dumb answers.
I agree. I think it's outside the box time. Okay, so Tim has pointed out that unfortunately the reason why we're having uplift here is because the San Andreas fault is, going right underneath us, and that will eventually rupture with severe effects. So thanks, Tim, for pointing that out. And then Claudette mentions that you said saving beaches for public use, but don't forget about the importance of beaches for shorebirds and other marine life, I would think.
Yeah, exactly. There's certainly it's a habitat, and that's important. Particularly the back beach where all the rack and the seaweed and everything collects and all those nasty little bugs that bite us that the birds eat. We got to take care of them.
Yep. I
How
see
much does
Sarah.
the tide gauge cost? That's a good question. We've been trying for X years to get one here. I finally convinced the city to buy one because we have one in Monterey, which is 25 miles away on granite. We're on sediments, and there's one in San Francisco, 75 miles north. So we don't know what's happening here. Finally convinced them to get one, and they've been spending, because of all the damage to our pier, they had to fix that, and they're still, I was trying to get it in for this winter and the El Nino, they're still installing it. They're not too expensive. I mean, it's on the order of tens of thousands of dollars. Once NOAA puts one in and they operate 12 along the coast, then they take care of it. But we talked to NOAA about doing, said, yeah, we're not interested in one. So, but they're recording, and as long as they're surveyed in very accurately and then resurveyed over time, because we're looking at tenths of a millimeter, it's not like putting in $5 million. They're pretty simple devices, pretty simple.
Yeah, simple, but if Gary Griggs can't get one in Santa Cruz, it's going to be a lot harder for us to get one in Noyo.
Maybe you have some heavyweights there.
Let's just face that right there. Okay, my stranding coordinator, Sarah Grimes, has a question. She has her hand up. She'd like to ask herself, it looks like. Go ahead, Sarah.
Yeah, I mean, you said there's a lot of dumb answers, and you brought up the Army Corps of Engineers.
Oh, no dumb answers.
Like, so
Right.
moving hundreds and hundreds of dump trucks worth of sand is just doing nothing but contributing to the problem. And using cement to build seawalls and move cities is like, that is a dumb answer. And it's making me freaking crazy right now, because it's like, no, we're not even thinking about looking at it. We're looking at like, let's go faster and destroy it faster and put up a silly little wall, like, and move sand. Sorry.
Yeah, no, that's exactly what's happening. And well, I'll beat up on the Corps of Engineers because I think they are a sort of a make work organization, and we're dealing with two problems they created here: a flood control project that wasn't done well, and a harbor that fills with sand. Too much sediment. And the fact that they've proposed this, I mean, one from New York to New Jersey for $120 billion. I mean, it'll keep them busy forever. But construction, you use concrete, making more cement adds more carbon dioxide. You've got all these machines pumping out. So I think I think they started out doing things worthwhile, like dredging rivers so that ships could come in and out. And then they went to building dams, which did work, and a lot of other fiascos. So you're right. It's really hard to think very far into the future. And I think for politicians, with a city council or a board of supervisors or a congressperson or senator, it's 2 years, 4 years, 6 years. And they've got 10 other problems breathing down their neck. It's the homeless people. It's the cost of housing. So these are relatively easy things to set aside. But then we have a winter like this one or last one. And fortunately, California is sort of pretty far ahead of the curve. We've had a lot of very environmentally conscious governors and legislators, and some new sea level rise bills. And I think because we are the world's 5th biggest economy, we have the longest coastline except for Alaska, the biggest population. other states and other countries even look to us for what we're doing. So I think we have an outsized impact in a sense. So whether it's our emission standards or our solar panels, we can influence more places maybe than we would if it's just the state. But still, there's this, people have just not had to deal with an issue like this before. COVID's going to go away. Inflation's going down, people are going back to work. Those are short term, but sea level rise is like centuries. And so, I mean, what do you do with a Miami Beach with hundreds of 50-story condominiums? Well, maybe you just fill the first 3 floors with concrete and you move the utilities up and you come in via a causeway or something rather than tear it down. But you may remember, I don't know, a year or so ago when that condo collapsed in Palm Beach with, I don't know, 100 and something people died, and it had been the seawater that's beneath them corroding the steel in the reinforcing steel in the concrete. And then the other condominiums began to start worrying about, whoa, what's ours like? But they keep selling these multi-million-dollar condominiums. So it's making money rather than thinking very far ahead. And I think, Florida for years had a governor that said, I don't want sea level rise being used in our reports. Let's call it tidal action. And you may remember we had a president before this one, and we have a U.S. Geological Survey group here that does coastal work, and all of their publications have to go through Washington and their center, and they were censoring out sea level rise out of all the reports under the Trump administration. So someplace it has to come back and bite you. But we're a pretty diverse society and diverse country. And so and I realize I'm in a bubble in a university, I'm in a bubble in Santa Cruz, I'm in a bubble in California, and I have to realize that other people have a very different set of information they work with, facts, alternate facts. So it's tough. I mean, this is my 56th year teaching, and I taught this morning and I realized how much more needs to be done. I'm now the longest serving faculty member. I don't want to retire. There's too many things left to do. Too many young students. I got to squeeze stuff into their head so they help solve the problems.
You can't retire, Gary. We need you. I think your point is a really excellent one, though, about the different timelines. Like politicians and city councils in all of these cities up and down California have a few years timeline in their projections. And I mean, we have an identity in California related to our beach life, and especially strong in Southern California, as you know. And a couple $100 million to nourish a beach that gets them through another summer is worth it to a lot of coastal cities because of the economic input it puts, that kind of tourism brings to their community. So it's really a challenging issue. It's super complex.
And it's one thing if the people there are paying for it, the homeowners, but if the state's paying for it, or in the case of the federal government, we're subsidizing Palm Beach homeowners. And we also subsidize farmers and a lot of things, but that's one, because I know something about it. I say that's the last place we should be spending our money.
Yeah. Yeah. Your criticisms of the Army Corps are heard. I keep thinking back to growing up in Southern California, going to Newport Beach, and my family had a house, or my relatives had a house on Balboa Island, and that island is surrounded by water, and they just keep rising, they just keep raising the seawall, but everybody's basements are flooding on the king tides. I mean, I don't know what a community like that's gonna do. I mean,
they're in trouble, Balboa and Newport. And if you go to that Surging Seas website, you can actually just bring in a foot or two, and all of Balboa Island goes underwater with about 2 feet.
Yeah.
But I don't know. That's Orange County.
Yeah.
They're in denial, probably.
They are in denial a bit. Yeah. I mean, that town is less so because they're seeing it every time they get a high tide. But yeah.
So they wanted to raise that wall 9 inches, thinking that was going to buy them 10 more years. And the engineer said, we ought to at least raise it 2 feet. And the people said, no, then I can't see over it.
Yeah. Yeah. It blocks their views, right?
Exactly.
It's amazing. And it's crazy the kind of thing they're doing just to suck up the seawater once it overtops the seawall.
Pump it back in and then pump it back in again. Yeah.
Okay, we had a couple more questions other than like commending you for a great presentation. Are
Yes.
you of related studies modeling the 10-mile dune area here, a fairly fresh formation as far as I know? So how could you could also change rapidly? That's a really good question. Like migrating dunes. We have a lot of dune habitat here. Some of it's been sort of stabilized by European beach grass, but what's your thoughts on the dune habitat?
So, I mean, we need a couple things to have dunes form. We need a lot of very fine grained sand. We need a flat, wide beach so that it dries out between the tides so the wind can blow it. We need a low area landward of it where the dunes can accumulate. They can't accumulate against a cliff. And we need a dominant onshore wind direction. And the main problems, I think, have been if the dunes are up against a barrier, a cliff, a road, they can't migrate. And if we cut off the sand supply by damming a river or taking the sand out of the river, we can eliminate the source of the sand. So dunes are vulnerable in many places, and we can do better by stabilizing them with vegetation. But I don't know that particular spot. I see the other question here is how the military reacting. They
That's
got big problems and they know about it. The biggest station in the country is Naval Station Norfolk, Virginia, and they're already seeing high tide washing up on the docks. All throughout the Pacific Basin, they've got problems. So they are very much aware of it. How they're going to react is a good question. They have billions of dollars to work with, but you know, I don't want to get into the military.
Yeah. Well, Gary, it's 7:30 and we've battered you with a number of questions. I appreciate you taking the time to share with us some of your recent work. I want to make sure everybody is aware that Gary has written 14 books. And Gary, you want to tell us what the title of the latest one was?
It's called California Catastrophes, the Natural Disaster History of the Golden State. And it's now in production. They say it's going to be out in August, so it's still got a ways to go. But most of the other ones are on the California coast. And if you go to, somebody made up a website for me, and it's just gary-griggs.com.
Nice.
And what's on there is every book I've ever published, the papers I've written, press releases, YouTubes of talks. I was surprised this guy found all this stuff and put it on there. So if you're really curious and really bored.
Well, we will do that because you referenced a paper just a minute ago that I want to get, and maybe we can put that up with your talk when we post.
One's on living shorelines and one's on resilient coastal communities.
Resilient coastal communities, because I think we throw that term around a lot. So I'd love to read your paper.
Well, good to talk to all of you, and thank you for the invitation.
Thank you so much, Gary. It's been great to see you again, and
I'll stop by when I'm in Fort Bragg.
All right.
Bye-bye.
We hope so. Thanks, everybody.